Today we're going to talk about experimental design. Couple definitions. First one's called an observational study. An observational study observes outcomes without imposing any treatment, and researchers don't assign choices, they simply observe them. Take an example. In 1981, researchers compared the scholastic performance of music students with that of non-music students at a high school in California. The music students had a much higher GPA than non-music students, 3.59 to 2.91. Not only that, 16% of music students had all A's compared to 5% of non-music students. The text example looked at the student of the relationship between music education and grades. Since the researchers did not assign students to get music education and simply observe students, quote unquote, in the wild, it was an observational study. Because researchers in the example first identified subjects who studied music and then collected data on their past grades, this is called a retrospective study. Had the researchers identified students in advance and collected data as events unfolded, the study would have been a prospective study. Observational studies are valuable for discovering trends and possible relationships. However, it is not possible for observational studies to demonstrate a causal relationship. I've developed a new rabbit food called Hippity Hop. It makes fur soft and shiny, it increases energy, and 100% of daily vitamins and essential oils. Can I make these claims? No. What must I do to make these claims? Do an experiment. Who or what should I test this on? Rabbits. What do I test? The type of food. So, an experiment. We're going to actively impose some treatment in order to observe the response. An experimental unit is the single, individual, person, animal, plant, etc., to which the different treatments are assigned. A factor is the explanatory variable. And the level is the specific level value for the factor. So we could have different values for each of the factors. The response variable is what we measure. The treatment is a specific experimental condition applied to the units, and that's the experimental units. I plan to test my new rabbit food. What are my experimental units? The rabbits. What is my factor? The type of food. And what is the response variable? How well they grow. So I use my pet rabbit, Lucky. Since Lucky's coat is shinier and he has more energy, then Hippity Hop is a better rabbit food. However, we have to have a control group, a group that is used to compare the factor against. It can be a placebo or an old or current item. A placebo is a dummy treatment that can have no physical effect. Placebos are the best way to blind subjects from knowing whether they are receiving the treatment or not. So now I use Lucky and my friend's rabbit Flash. Lucky gets Hippity Hop and Flash gets the old rabbit food. Wow, Lucky is bigger and shinier, so Hippity Hop is better. When we know what treatment was assigned, it's difficult not to let that knowledge influence our assessment of the response, even when we try to be careful. In order to avoid the bias that might result from knowing what treatment was assigned, we use blinding. There are two main classes of individuals who can affect the outcome of the experiment. Those who could influence the results, the subjects, the treatment administrators, technicians, and those who evaluate the results, the judges, treating physicians, etc. So blinding, method used so that units do not know which treatment they are getting. And then there's the double blind. Neither the units nor the evaluator know which treatment a subject is receiving. So the first 5 rabbits that I catch will get Hippity Hop food, and the remaining 5 will get the old food. The hippity hop rabbits have scored higher, so it's better food. So the principle of experimental design, we have to have a control. So we control the effects of extraneous variables on the response by comparing treatment groups to a control group, a placebo or an old version of the treatment. We have to have replication. Replication of the experiment on many subjects to quantify the natural variation in the experiment. In other words, if we just had one subject, it could be just that this subject would do better than others. If we have many subjects in this and our treatment makes it better, then it has to be the treatment. We have to have randomization, the use of chance to assign subjects to treatments. We can't just pick who we want to go in the hippity hop food versus the old food. And then we have the block. Sometimes attributes of the experimental units that we are not studying and that we can't control may nevertheless affect the outcomes of an experiment. If we group similar individuals together and then randomize within each of these blocks, we can remove much of the variation due to the difference among the blocks. However, blocking is an important compromise between randomization and control, but unlike the first three principles, it's not required for an experimental design. So we number the rabbits 1 to 10, place the numbers in a hat. The first 5 numbers pulled from the hat will be the rabbits that get hippity hop food. This is our randomization. The remaining rabbits get the old food. I evaluated the rabbits and found that the rabbits eating hippity hop are better than the old food. The only way to show cause and effect is with a well-designed, well-controlled experiment. Let me say that one more time. The only way to show cause and effect is with a well-designed, well-controlled experiment. One more time. The only way to show cause and effect is with a well-designed, well-controlled experiment. Let's take an example. A farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizers. 15 similar plots of land are planted with the same type of seed, but are fertilized differently. At the end of the growing season, the mean yield from the sample plots is compared. So what are my experimental units? The plots of land. The factor is the type of fertilizer. The levels, fertilizers types A, B, and C, since there's 3 types. Our response variable is the yield of the crop, so I have 3 treatments. Our second example, a consumer group wants to test cake pans to see which works the best, in other words, bakes evenly. It will test aluminum, glass, and plastic pans in both gas and electric ovens. Our experimental units are the cake batter. Our factors, we have 2. We have the type of pan and the type of oven. For our levels, the type of pan has 3 levels and the type of oven has 2 levels. The response variable, how evenly the cake bakes, and our number of treatments is 6. So we can show that with a tree diagram. We have our cake pans. We have the 3 types, aluminum, glass, and plastic, and each one of these are going to go into an electric and a gas oven. So there's our 6 treatments. Aluminum with electric oven, aluminum in a gas oven, then we have glass in an electric oven, a glass pan in a gas oven, and plastic in electric and gas. And then what we do is we compare the results.